the mute all button.
Except me, perhaps, at some point.
Yes, yes. I'm gonna. Is there a mute all button? Oh, there it is. I had to hover. All right, and then. It doesn't work. Technical difficulties. All right, I'll just mute by hand.
Muted.
Just ask everyone to mute himself or herself.
No, I can do it one by tagging everybody muted. So, okay, it should be done now, and I'll turn it over to our president.
Okay. Hi, just a couple quick notes. On Monday night, as I told a couple people that were here earlier, on Monday night, the SFA was asked to be part of a documentary that the BBC and PBS were filming. And we had about 15 members come. Even in the rain, we had, I think, 6 telescopes. And Bill came with his EV scope. It was fantastic. The weather did sort of work out. The skies were a little gray, and all of our members were fantastic actors. I will give everyone props for that, pretending like we could actually see the night sky. So that documentary will more than likely be coming out in January 2023. And it will be airing on PBS. Once we know more details about that, we will let everyone in the club know. Also, the voting for the 2022 board is still open. If you have not voted yet, if you're a member and you have not voted yet, please do so. And then someone asked earlier in the chat about streaming. Once we return to in-person, which we are working on with the Randall and with the new board, we will do everything in our power to continue to stream our lectures because it aids in accessibility for members and non-members and guests. And it also allows people that are not in the Bay Area to attend our wonderful lectures. So that is dependent on the internet at the Randall, but we are doing everything to work with the Randall so we can stream. And then our 2022 members only Star Party dates hopefully will be finalized in the next couple of days. I can say the first Star Party will be January 29th, which is a Saturday. But for the rest of the year, that as soon as we get the permits back, I will let everyone know and it will go on our calendar on our website. So now I'll turn it over to Linda.
Thank you. On January the 19th, 2022, celebrating San Francisco amateur astronomers' 70th anniversary. Join us then for, as longtime members of SFAA share their experiences with the founding of our organization, focusing on bringing astronomy to a wide amateur audience. Members and the public enjoyed star parties with SFAA, lectures, telescope making. At that time, early, it was at the Wallace Telescope Makers Workshop. The very first lecture was held at the Josephine D. Randall Museum. And it was an exciting time in the Bay Area for public astronomical learning at that time. And so we'll have some very, very interesting talks and memories of the founding. On February 16th, Shocking Origin, Meteor Impacts and the Chemistry of Life by Ariana Gleason Holbrook of Stanford and SLAC, the National Accelerator Laboratory. When and where life originated on Earth, and if or where life exists elsewhere in the cosmos are some of the biggest unanswered scientific questions of our time. Using SLAC's X-ray free electron laser, we will learn how the process of shock compression may hold the key to revealing the origin of life, February 16th. Always on third Wednesday, and I hope you'll join us then. Tonight, we have with us Dr. Keith Fong. I'll give you information about her. She obtained her doctorate in astrophysics at the University of Chicago in 2015. She worked as a JSI postdoc fellow jointly at the University of Maryland and NASA Goddard Space Flight Center from 2015 to 2018. In 2018, she was awarded NASA's Einstein Fellowship, which brought her to Stanford University in 2018 to pursue her own research program. Earlier this year, she moved to University of Wisconsin-Madison as an assistant professor in the Department of Physics. She pieces together the information we receive from the universe from a multitude of messengers. including high energy gamma radiation, ultralight particles known as neutrinos, and cosmic rays to study the extreme activities of the universe. We look forward to Keith Fong's presentation, Not So Fast Supernova, highest energy cosmic rays detected in star clusters. Join me in welcoming her tonight.
Thank you so much for the introduction. Let me share my screen. All right, is this all good?
Yep.
Okay, cool.
Thank you.
All right, so hi everyone. It's a great pleasure to join you tonight and tell a bit about the cosmic ray story that we have been excited about. The front page here is showing you a imaginary picture of the cosmic rays, which I'll tell you a bit specific about what the meaning about cosmic ray. But had our human eyes been sensitive to the energy that this cosmic ray particles coming from the universe, then this would how we see from the night sky. So you would see this gigantic shower-like particles generated from the atmosphere of the Earth, and you'd see these gigantic showers one in a while, and this would be and for reference, there is some small detector on the ground that is human height level, and these are gigantic flashes from the outer space that arrive to our Earth from time to time. Okay. So cosmic rays, these are essentially the outer space messengers, as I just mentioned. These are rays, and cosmic means cosmic, they are outer space. Now, these particles, I'm telling you these are particles, but back in 100 years ago, it was unclear what these things are. First of all, these are radiation. So these are like you feel when you have a counter, you would see that there are radiation being produced for this particle constantly from the ground. So there was back then a debate whether these radiation are coming from the Earth itself, or is that coming from outer space. So that's when Vector Haas, this brave gentleman on this picture on the left-hand side, got himself onto a gigantic balloon where he launched himself into a height that's 5 kilometers. And at that height, he finds that the radiation at that height is twice that at the sea level. And therefore, that suggests that these are essentially a radiation coming from an outer space, not coming from the Earth, because the further you are, the higher of the radiation that would be you would experience. And this was essentially the Nobel Prize in 1936. Well, it was quite an achievement because the height that he reached was this balloon-borne open flight, was already actually about half, almost more than half of the current height that the commercial flights would go. So just imagine yourself sitting in this open cart going to that high distances. So what with the picture on the left-hand side is showing that these outspace radiation is going to be higher and higher as you move to even higher height, and on the ground level you're really experiencing a lower level because the Earth's atmosphere has been blocking most of the lower energy radiation and interact with high energy radiation to break them down into lower pieces. But still, this is the meaning of the cosmic. It's not local, it's some outer space origin. But back then, people were still debating whether these rays, this radiation, are photons or are they actual particles. So you can learn from the name, the rays, that is what people usually refer as photons, radiation. So people had a long time argue that these must be photons, until in 1930s and 1937, Ross and Auger was able to identify the nature of these cosmic rays as particles. And the reason is actually pretty simple. is that the differences in the intensities of these cosmic rays arriving from the east and the west part of the Earth there's a difference. And we know that our Earth has a magnetic field. So the reason to cause this intensity differences would be that the cosmic rays are actual charged particles, so that they are interfering, they're confined by the magnetic field, their eventual arrival direction on our Earth has an effect, being affected by the magnetic field. And that's how back then people know that these rays must be charged particles. So this particle has been known for about a century now. And among these detections and observations, the most energetic particles in the universe has been observed to come with an energy of about 10 to the 20 electron volts. So this seems to be a big number, but maybe all the astronomical numbers looks big, so it's not that impressive. Even back then, when people receive it, the scientists were calling these cosmic rays as the "oh my god" particles because of their huge energy. So to give you a sense of what the energy looks like, the man-made accelerator, the largest man-made accelerator, which is the CERN LHC, Large Hadron Collider, is circling in several big towns, and the maximum energy that it can reach in this Hadron Collider is only 10 to the 14 electron volts with a center of momentum frame. So this is still 1,000,000 times lower than these particles that we see from the nature. In other words, to learn particle physics above this energy, we would have to turn our eyes into the nature, into the universe, to the night sky, because the LHC is already quite an achievement by having its gigantic size. And if you would make another order of magnitude bigger, you would have to circling almost a whole country for this gigantic linear accelerator. And it's hard to reach the level of energy that the universe is sending to us. If that still does not impress you, the kinetic energy of a spinning baseball is at the level of 10 to the 20 electron volts. But a baseball is composed of at least 10 to the 23 number of atoms. If you think of compressing those 10 to the 23 number of atoms into just one particle, and that is actually the cosmic particle you get from the universe. And that's the level of the energy that we receive. So these are truly impressive particles. And specifically, the discovery of the first "oh my god" particles was discovered by John Leslie in New Mexico in 1962. And this is on the left-hand side shows John Leslie with his little looks like very crappy, but it's actually a serious detector buried under there for detecting one of those particles. And how do you detect them? So that Sirius detector, which is actually a prototype of the modern day detectors, goes like this. So essentially you have a kind of a container where you put up a photomultiplier, and the cosmic rays comes in, and you want a scintillator or some kind of a material to allow the cosmic ray to pass through. So the cosmic ray, when the cosmic ray passing through the scintillator, they're going to generate multiple photons when it penetrating the liquids. And these photons could be captured by the photomultiplier inside your detector. And how many photons is produced is related to how energetic these particles are. And the direction where you receive these photons would be sensitive to the direction where the cosmic ray come from. So that's essentially the basic mechanism of the cosmic ray detectors. This is for individual ray when it goes through one of your detector. But when the cosmic ray has a really high energy, remember the first slide was showing that such a big gigantic air shower is developed. So that's when you need a bunch of detectors separated with big distances to see the full structure of the air shower of the whole ray. Because the particle comes in and they are so energetic, so they're not going to travel all the way to the Earth. But before that, they would already interact with our Earth's atmosphere and producing a bunch of secondary particles, that's this shower. So you would need an array of these water tank detectors, this liquid scintillator detectors, to capture the secondary arrays, this big showers of the whole primary cosmic ray. So here I'm showing you a demonstration of the Pierre Auger Observatory, which is an observatory at the southern hemisphere at the border of Argentina and Chile. So this detector covers a total surface area of 3,000 kilometers square. And each of the gray dots is a water tank array, as showing up here on this right, on the photo on the top right. And each of them is an individual detection unit with the mechanism I showed in the previous page. And on top of that, there are 4 Florence detectors at the edge, which is sensitive to the Florence light generated when the cosmic ray entered the Earth's atmosphere. So when an energetic particle comes in, the ground detectors, these water Cherenkov detectors, would be sensitive to collect the photons generated when the secondary particles penetrating through their liquids, while the 4 Florence detector would be able to see the Florence light when the particle goes through the Earth's atmosphere. So that provides as an independent construction of the original arrival direction of this cosmic ray. In the Northern Hemisphere, there is also a similar detector, although with a much smaller size, about a quarter size of the Auger Observatory. This is the telescope array in Utah. This telescope array within this country covers 700 kilometers square. These blue dots are essentially the individual water ground-based detector. And they also have 3 Florence detectors as indicated by the red dots. And these are essentially the telescope that it behaves, it's the same technique as the Auger, but it's a much smaller size. On the right-hand side, I'm showing you a movie for the image of the ground-based array. When a cosmic ray particle comes through, you would see something like this signal passing through your window. And because the cosmic ray covers a whole energy, the lower energy cosmic rays would also showing up like as the background. So you would always see some background radiation fluctuations. But when a signal comes in, you can see that it flies comfortably through your window. So as you can see, these are not traditional telescopes, but these are our telescopes are using a very different way of looking at these particles. And they cover a much, much bigger area than a normal optical telescope. So with all of these gigantic telescopes on the Earth, actually the Pierre Auger is the largest observatory of astronomical observatory in the Earth. So with these gigantic telescopes, what people have been seeing over the years for both telescope array and Auger has been operating for comparable or more than 20 years now. And this plot here summarizes the observations from the Pierre Auger Observatory in the Southern Hemisphere. So, so this is a professional plot that goes through it carefully, step by step. So the y-axis here is showing something as we call it as an intensity. So that is essentially the number of particles in a particular energy bin that arrives the Earth per unit time, like per second, and per solid angle, because we are looking at the different part of the sky. So if we would look at a particular direction per unit area, that is the intensity. And in addition, we have scaled the intensity by energy cube. And that is a mathematical way to shrink the y-axis to be more visible, to see the smaller features, because we are looking at a bunch of particles comes with drastically different energy. The x-axis is the energy of this particle in logarithmic scale. Don't worry too much about these mathematical details, but these are essentially the energy of these charged particles that the detector reconstructs. And on the top is just the energy in non-logarithmic scale. Now, the numbers on top of these data points are the number of particles that have been detected in each of these energy bins as of 2015. The detector is also updating as a function of time. So by 2021, we have slightly more events. But the key point here was by 2015, there has already been enough statistics to show that this is a very well measured spectrum, which shows several interesting features. The first of which is around the energy of 5 times 10 to the 18 electron volts. So somewhere here, if you can see my pointer. And this is where the spectrum changes, like the shape change. You can see that below that energy, the spectrum is kind of a flat spectrum. It's like a power law. It's a linear thing in the logarithmic scale. But then after that point, there are some feature, like some additional thing comes in and the flux goes up. So this point is what we normally refer as an ankle in this spectrum, like the human's ankle. And this ankle is usually interpreted as the point where the sources inside our, like the emission from the sources inside our Milky Way is transiting into sources outside this Milky Way. And above that energy, another feature is above 10 to the 19.5 electron volts. That's where the spectrum cuts off. So you can see that shortly above 3 times 10 to the 19 electron volts, the number of particles you collect drops down very quickly. And specifically, when you go above 10 to the 20, there's only 5 total particles being detected by 2015, which is like 15 years of operation already. So these features, this is the drop-off feature that I mentioned. So this particular feature has been understood as a cosmological termination. The reason is that when we look at the full sky, the night sky, if had our eyes been sensitive to microwave band, we would see a gigantic, uniform, distributed cosmic microwave background. And I'm sure you have heard about this from previous speakers. And this cosmological background, this radiation comes from very early time of the universe. And because the universe has been expanding since then, the emission is quite uniform. It exists till very early universe. So, but the particles we are looking at with Auger and telescope array are so energetic that they would interact with these cosmic microwave background. This interaction is going to produce a bunch of secondary particles, which I'll mention later. But the direct effect is that this interaction is going to kill this most energetic particles that travel from a distance that's more than 100 megaparsec away. So that makes it a horizon of the particles that we see. So anything beyond this distance can hardly be observed, or that's why you see like the population drops very drastically above the energy where the interaction would happen. Now, what is 100 megaparsec? That is roughly 321 million light years. Our Earth is here. We're inside the solar system. Solar system is somewhere at 8 kiloparsec away from the center of our Milky Way. Our Milky Way itself is part of this local group that has several other galaxies like Andromeda. And this whole local group is another small portion of the local supercluster called the Virgo cluster. So we are here, but the 100 megaparsec is roughly the local supercluster where the sources would fit in. So if the cosmic rays come from distance more than further away from the supercluster, like the early universe, we would not be able to see them at such high energy. Therefore, we are seeing something that's coming from kind of local, but further away, definitely further away from our own Milky Way. Okay, so just go a bit further. We are here. Like I mentioned, we are in this local supercluster called Virgo, and that's our local group specifically. If we want to zoom out to see the whole universe, then we get a bunch of superclusters nearby, like the Comma and a few others. And so we are really seeing this little grayish box when we're looking at cosmic rays at such high energy. All right, so that's the number or the spectrum of these cosmic rays. But there are additional things that these the observation of these cosmic particles are telling us. One of them is the cosmic chemical composition of these cosmic rays. So when the telescope observes the air shower that's generated by these cosmic rays, the shape of the air shower, or specifically the depths of the air shower, how fat they are at different distances, is sensitive to the chemical composition of the cosmic ray. So in this plot here, we are showing the specific atmospheric shower depths as a function of the distance that the particle penetrates through. And you can see that the different color indicating different particles, all the way from photons to protons to ion. So although there are some overlap between proton and ion, the peak of them and also the width of this air shower would be different from composition to composition. So specifically, when the air shower comes in, and on the left-hand side, we're showing the top left one is as if you are seeing an air shower dropping from the zenith. So you're seeing this whole shower generating. And then this bottom and the right plot showing a 3D projection, if you would look at the height as well as the development in the x direction, in how fat it is. So as a function of time, as the time goes up, you would see that you would get different type of particles, and the hadrons would always be more contained. Electrons would definitely be much fatter, and you also have a bunch of neutrons and muons that can be used to tell the initial particle based on the physics that we understand of the particle interaction with the air. So through this physics and by this measurement, we would be able to find out the chemical composition of the primary particle that goes into the Earth's atmosphere. On the right-hand side, there is a summary of the measurements of Auger for the chemical composition. So the data points are the measurement, and the red curves are the measurement, how the measurement would be had the particles being protons, and the blue are the Xmax, or the atmospheric shower depths, had the particles being pure iron. And there are different lines because we have different interaction models. Remember, again, these are beyond the human-manned accelerator. So these are essentially a bunch of physics that cannot be tested by man-made labs. So these are physics that are extrapolated from the known physics level down at 10⁻14 electron volts and extracted to this high energy. So you can see that the chemical composition of these particles would started off being mostly proton-like light element, but then as the energy goes up, it would gradually transit into a heavy composition. And this is an interesting feature that has not been explained yet by the series. Another exciting thing about these particles is the arrival direction. And in 2019, the Auger Observatory report an interesting feature, which is that the particles comes with a particular large-scale structure. So the color here indicating the dipole moment of these cosmic rays, or specifically you can think of as if you are removing the universal component. When you're subtracting some universal component from the full sky, you would start to see that some region of this sky, as indicated by the red, would have more particle arrival than some other region, as indicated by the blue. And particular, sorry about that. And in particular, the star is where the galactic center locates. So you can see that the particle has a preference of their arrival direction as anti-galactic. So it's suggesting that these particles are not from our own Milky Way. Okay, so that's a lot of explanation about the detection of these cosmic rays. So we have detected most of them, but still it's very hard to understand where the particles come from. And this is because that the particles do not travel in a straight line. So let's look at the source hypothesis. So there are different sources that can make these high energy, oh my God, particles. The black hole jets is one of them. And when the black holes, supermassive black holes are accreting, the supermassive black holes are accreting, that they would get mass surrounding the material and they would eject out this accretion of material is going to spell out the stuff out, and this matter coming out with a very quick velocity are the jets of the black hole. So these jets are super energetic. That's why they can accelerate particles. A second possibility are the large-scale accretion shocks. From the intercluster medium. So this is a simulation result. These are a bunch of previous TIPAC, Stanford TIPAC public lectures that are on specific subjects for your reference. And these are big, gigantic accretion shocks around the superclusters of the universe. And then neutron stars, for example, the Crab pulsar, which is a very nearby bright source in all wavelengths. They are also compact objects and they are also energetic, providing potential locations for particle acceleration. And finally, it's hard to know which of these sources, or if any of them at all, are producing these particles. And the reason is that these particles are charged, so they do not travel in a straight line. And so this is a picture to give you some sense about this idea. Here is a sketch of our own Milky Way. Our Milky Way has a disk-like feature with all the stars sitting on the bulge and the disk. But in fact, the Milky Way has more content that is less dense and is actually having a halo. And the magnetic field is all contained in this Milky Way halo. So when a distant source of this cosmic rays that shine, we would normally see the photon travel in a straight line because photons are neutral particles. But the particles, the actual cosmic rays, because they are charged, they would not travel in a straight line, but instead they would go through deflections. Sorry about this, it's very dry here in the room with the heaters on. So the particles would travel in a non-straight line because of the magnetic field. And if the particle has a low energy compared to has a relatively low energy, then it would essentially be confined and gyrate and essentially lose their original direction, but when the time they reach the Earth. So despite that, centuries of effort has been putting in measuring this cosmic rays, we still do not know where they come from. And that's why to fully understand where they come from, we need to find in the ash of the smoking gun. And one way of doing them is to look for the secondary particles that are produced when this cosmic particle propagate to our Earth. So let's look at the messenger called photons. So when a cosmic ray travels through the intercluster medium and the interstellar medium of our galaxy, it would interact with a background particle and producing a bunch of so-called secondary particles, including photons and neutrinos. Photons are essentially light, and neutrinos is a weakly interacting neutral particle. So both of them would trace back to the original direction where the proton would comes from, whereas the proton itself would lose its original direction and generating air shower. So by looking at the photons, we would be able to identify the sources of these cosmic rays. So there are different ways to detect these photons, and there are in space. Fermi, which is one of the satellites of NASA, has on board is a free flyer that carries a payload that can detect the electrons and photons generated from the space generated from the universe and collected in the space. There's also ground-based detectors such as the HASS, MAGIC, and Veritas. These are essentially a bunch of telescopes that are using imaging technique to see the gamma rays, the photons at very high energy. And there's also a water tank detector called High Altitude Water Cherenkov Observatory in Mexico at an altitude of 4,000 meters, collecting the gamma rays coming from the space. So the sky would look like this was in the eyes of a photon in the GeV band. So this is a night sky detected by the space telescope Fermi. And we can see that there is a very bright galactic plane. That's the plane that we are on, that has a bunch of different sources and also some dust features. And in addition, on the high and below, above and below the plane, we see lots of point sources, these bright dots. And these are believed to be more distant AGN, like black hole jets from more distant universe. And in particular, there is this interesting feature of the Fermi bubble above and below the plane, this big, gigantic bubble inflated by the jets of our own galaxy, of the black hole of our own galaxy. So the TeV sky, or in the energy that's higher than the Fermi-Lab telescope is accessible to, we have been able to see the sky using the ground-based detectors, including the HAWC. And in this high energy, what we see is a galactic plane again inside this white dashed band. And most of the sources at this high energy are essentially from the Milky Way. And we also see some sources that outside the Milky Way, specifically two blazars, which are black hole that jets are pointing toward us. So we see many interesting sources with this high energy gamma ray telescope that includes a bunch of like this highest energy sky. You see a bunch of pulsars. So these are the neutron stars. We also see a mini active black hole that's next door. And this is the SS433 X-ray binary. It's extremely bright in X-ray. And it's one of the brightest X-ray binaries in the night sky. And this is somewhere there. If we zoom in, we can see that the black hole is a 10 solar mass black hole with a donor star, an OB type donor star with a 30 solar mass. And the black hole itself is extremely tiny, but it extends a gigantic extended X-ray, a set of X-ray jets piercing through the remnant surrounding the black hole. And with the HAWC, the gamma ray detector, we were able to see a set of gamma ray jets from this particular source as well. And the gamma ray emission happens to be located at the position where the X-ray emission would come from. So the right-hand side is showing you the same source in the eyes of a radio telescope and an X-ray telescope. So the radio telescope shows that there is essentially a fish shape of remnant, which is the material ejected at the same time when this black hole was formed from a supernova explosion that's more than 40 kiloyears ago. And the center is the black hole. In the X-ray image, you see clearly there is this gigantic jets shooting out from this black hole. And the gamma ray emission detected by the HAWC observatory also comes from this bright X-ray emitting spots. And then the other very interesting source that we detected lately is the stellar cluster. So see, this is the Cygnus cluster. And what I'm showing here is the Cygnus constellation, which is essentially a very beautiful, elegant Cygnus. But the stars are not necessarily coming from, they're essentially uncorrelated with that big distances. But at the body of the Cygnus is a cocoon called Cygnus cocoon. And this is a set of a cluster, like a very 2-degree extended kind of a bubble or cocoon that's inflated by starburst activities. So on the left-hand side here, I am showing you an infrared image of the Cygnus cocoon. The white dots are a specific bunch of stars, star clusters. Each of them are individual OB type of stars. And there are actually more than two, but several stellar clusters in that region. And the colored image indicating the dust emission from the region. And you can see there is a very clear boundary out of this cocoon, and suggesting that this is a feature that's attached to those stellar star clusters, and it's a natural cocoon that's inflated with these activities of these stars. Now, with the HAWC, we were able to identify gamma emission from this gigantic 2-degree cocoon. So on the left-hand side is the infrared map that you already see in the previous slide. And on the right-hand side, this is the same coordinate, but with the image indicating the gamma emission from the region. So the colors indicating the observation of HAWC in very high energy gamma ray, so with energy above 10 to the 12 electron volts. And the dashed contours indicating the GeV, so 10 to the 9 electron volts gamma rays observed by the Fermi-lab observation. So you can see that both gamma ray detectors seen emission from this gigantic cocoon, and the cocoon itself has a feature that's consistent with the dust emission, with the morphology of the dust. So a little bit of a more scientific assessment suggests that these gamma rays are likely coming from protons that are accelerated by these stellar winds and interact with the dust in the region. So this is a very exciting type of so-called pevatron, PeV accelerators that the gamma ray experimentalists have been hunting for years, because we see those PeV cosmic rays, but we barely see them in the gamma ray sky. Right, so that's the nearby accelerators that goes to 10 to the 15 electron volts, not yet to the ultra high energy in the first part of the talk. So let's spend the last few minutes about the other type of the smoking gun, which are the neutrinos. So neutrinos are neutral particles. They are actually the first part, being named as the first particles because they are weakly interacting, meaning it's very hard to capture them. So that's so far a lot of experimental efforts has been spent in understanding and capturing these first particles. And Cube Observatory in the South Pole is one of the detectors that has so far successfully measured these high energy neutrinos. And Cube is a detector that is buried at the geographic South Pole, buried under the ice for more than 2.8 kilometers down the ice, go all the way to the bedrock. And this is the Eiffel Tower out there for reference of how gigantic this telescope is. And when a neutrino comes in, it's going to interact with the ice and producing a bunch of photons and lights that the photomultiplier sensors along the strings of the IceCube detector could be sensitive to. And the first detection of the neutrinos was so excited that the experimentalists give them specific names. That's Ernie and Bert. But now, after a few years, we have detected so many that we don't care about them anymore. And on the right-hand side, it's a summary of the individual events that has been seen over the years. And the future would be to build up even bigger detectors, like 10 times width of the volume of ice cube, to see these neutrinos. And there's also other detectors being planned from either to detect these neutrinos from either space or on the ground using mountains. And so, right, so I would just stop here, and in case people are interested about future, I can go get back a bit more. But to conclude, this is a very interesting time for the cosmic ray, neutrino, and gamma ray observers, because we are, for the first time, sitting in a multi-messenger era, where we see the sources not only through the lights, but also through particles and through neutrinos. And each of these different type of messengers sent by the universe carry a very different perspective of information that can be combined and synchronized to understand the universe. All right, thank you. I'll stop here and take questions.
Wonderful, thank you. Well, we do have some questions in the chat, so I'll start with those. And if anybody else wants to ask a question, you can raise your hand or put it into the chat. We have the first question from Jeffrey. Are the cosmic rays detected by the high altitude water Cherenkov observatory composed mostly of protons or electrons?
So Hawk sees cosmic rays as both electrons and cosmic rays, and like protons, and it actually see more than protons. It also see helium and carbon, oxygen. So the chemical composition of these cosmic rays changes as you go to different energy ranges.
He follows up with, what detected proportion of cosmic rays reach PeV levels?
What fraction? Yeah, it depends on, so for Hawk, it's sensitive to cosmic rays above energy of 10 to the 12 electron volts, but the cosmic rays, the distribution follows a power law. So the higher you go, the number of particles you see is much, much smaller. So one way of looking at it is to using this map that I see much earlier. For example, here, this is a representation of the power law spectrum. It's not quite the PeV energy that you're asking, but it gives the reference about how it goes. So at the Hawk energy, the spectrum would fall down roughly like this band, e to the minus 2.7-ish. So you would see that if you started off with like 22,000, then with about 10 times higher in energy, you would decrease to at least 3,000, so 7 times lower when you go to higher energy.
Jeff has another question. How are parameters of detected secondary rays used to reconstruct the parameters of the primary ray?
Yeah, that's a good question. So it's not a simple thing. In fact, so what this movie shows is a good demonstration of what people would do. So in reality, what people would do is for individual events, for each of the events, you would see this kind of time evolving structure of individual air showers. You would record them, and then you would compare them to a simulation, which you constructed using a setup of your own detector, and a imaginary particle comes in. And you would compare the air shower generated by your simulation and the actual observation, and compare them at different snapshots in time, and use that to determine whether my hypothesis about the initial composition is comparable to what's the best fit model that explains my observation. From that, you can determine what's the initial composition, for example. So in this whole process, is the physics taken into account in the simulation that would account for both the prime rays and the second rays, as well as their time evolvement.
Mm-hmm. There's someone on YouTube typed something, but I can't quite make out. So viewers on YouTube and Facebook can type into the chat there also. Going back to the chat on the Zoom from Jeff. How can we be sure that the high energy cosmic rays from a cluster like the Cygnus cluster are the result of forces, winds, magnetic fields within the cluster, rather than a supernova explosion within the cluster. Are the stars in this cluster too young to have undergone supernova?
Yeah, that's a really nice question. So this is a OB2 star cluster region, and in the and there is indeed a supernova remnant in gamma ray band that has been observed. That's actually in this purple region. If you can see, it's a pretty dark. This is the gamma Cygnus supernova remnant. So yes, supernova remnant has happened in this region before. However, the emission we see, the energy of the supernova remnant is insufficient to explain the whole emission from this whole region. So that's why we know that it's not individual sources, but it has to be the whole contribution of the whole stellar cluster in that region.
Okay, we have another question from Jeff. Star clusters like Cygnus OB2 are thought to be formed in the aftermath of supernova explosions. Is the energy of cosmic rays generated by these star clusters proportional to the energy of the supernova that was the source of the star cluster?
So these are OB stars, so they are like our own sun, and they have not gone through an explosion yet. So these are ordinary stars. And these stars also have winds. So that's the wind, so the exerted energy, and that's how the whole bubble is formed. And when we compare the energy of the gamma rays that we see with Fermilab and Hawk, and the total optical energy carried by these stars, we find that the energy of the gamma rays is a small fraction of the total energy carried by these stars. So they could be able to have a small fraction of their total energy goes into the particle acceleration and later produce these gamma ray emission. However, there is an interesting point here, is that we said earlier that the galactic magnetic field would be able to confine these particles. So there are zombie cosmic rays being contained in the galactic magnetic field. So these cosmic rays may also interact and producing gamma ray emission. But what we see with the gamma ray emission, gamma ray observation, is that these flux we observe from this region, it's so high that it cannot be explained by this zombie cosmic rays. So it must be something that's local to this region, accelerated exactly by these star clusters.
Do we know what the strength of the magnetic fields within OB clusters are?
We do not know exactly, but we could infer from the temperature of the dust in this region, which is comparable to 20 microgas, which is like 5 times higher than the average of the ISM, the interstellar medium.
We have a question from Marilyn. Can you explain more about the particles that consist of intact atoms?
Consists of what?
Of intact atoms, atoms that are intact.
Oh, so this might be a demonstration page. I didn't go through the details of these interactions, but essentially these are extremely energetic particles that they are definitely a nucleus, and they have when they are interacting with a background particle at such a high energy, it's like a bag of quarks that are interacting and recombining into different processes. And this whole process is going to generate lots of different type of secondary particles. But through particular interactions, like when the proton at particular energy is sensitive to, they're going to producing different types of secondary particles like gamma rays and neutrinos. And these secondary particles, these products from the interaction, is what we used to trace back where these particles were coming from.
Okay, we have a question again from Jeff. Do other parameters of a star besides mass determine the strength of stellar winds?
So the strength of the stellar winds itself is, especially how they make these energetic particles, is still an active round of study. We do not have a firm answer to how particles get accelerated in its stellar winds. Actually, this result of the stellar cluster is a bit surprising in the sense that when we usually think about these particles at such high energy, we would think about like neutron stars or black holes. Those are extremely bright in gamma rays. They're super energetic. But what we see here is just ordinary stars. And that's why it's quite surprising. Like we detected for the first time that these things shine at such high energy, but how they make this emission is still an open question.
Mm. We've got one more question from Jeff here. Oh, I see a raised hand from Terrence. I'll go to you, Terrence. Go ahead and unmute you.
There we go. Can you hear me?
Yes.
All righty. I had a question on this slide. You earlier talked about the effect of the magnetic field of the Milky Way and also the Earth's magnetic field on causing the charged particles to be deflected. I don't know whether this is artistic license in this illustration, but it seems like both of those magnetic fields are well studied and predictable. And so can't you correct, wouldn't it be a correctable and understandable way to get the original direction? I don't imagine that the particle actually wanders around quite as much as this slide indicates, but can't you correct for and predict the source direction by factoring in the known magnetic fields that are fairly stable?
Yeah, so unfortunately, the galactic magnetic field is not known to that good extent. We have some ideas about how the magnetic field look, but not to a level of goodness that we can reconstruct the original direction of these particles. Another complication is that the gyration of these particles and that depends on the turbulent structure of the magnetic field at particular location. So when the particles, say, if they gyrate a little bit at this point, depending on how the detailed structure of the magnetic field is at that point, they may either go this way or the other way. And that would be just one vortex. But when the particle at this energy reaches our Earth, it depends on energy for sure. So if it's like, say, 10 to the 18 electron volts, it would typically be delayed for a time of over thousands of years, spending in this magnetic field. So lots of gyrations. It's impossible to construct where they were initial. After that many runs, it's impossible to construct where they were initially coming from. But for the ultra high energy cosmic rays that we learned, like the oh my god particles, because their energy is so high, their gyration is like a small rectilinear travel through the galactic magnetic field. So those are easier to be reconstructed. So that's how we know from this anisotropy map that we see, even these are charged particles, but their arrival direction at such high energy can still indicate some information. And when we see that the galactic center is not in the favored region, we can conclude that the sources are not in that region, exactly because we know some structure of the magnetic field of our own galaxy that at this level, at this high energy level, we can reconstruct their original direction. And so that we understand the origin is not the galactic center.
Got it. Thank you.
Let's go to Tom next. Tom.
Dr. Fang, I really enjoyed your talk and your energy. And
Thank
I can't think of any specific question because some of it went over my head. But my specific question is, do you know at what age and what event, was there one event, one teacher, or something that kind of nudged you in the direction of going where you're going? Because clearly you are just loving this material. And so I just kind of wondered what brought you in this direction.
There are many motivations. And actually, I was in an amateur astronomy association when I was in my undergrad. And I majored in physics. And then I decided that the astronomy is the dream. So then I started to pursue a graduate school in the astronomy direction. And as a one way, never go back after that. But even when I was young, my parents got me a set of refractive telescope to look at the moon and the Saturn, and that was the initial motivation about the real interest in this. So I'm really glad that I continued in this direction over the years as a professional. Like, sometimes it's painful to look at the data and do analyzing and find bugs in your code, but these interests definitely hold me up through those moments.
Excellent, thank you. We had one question left from Jeff, but anyone else, feel free to raise your hand. From Jeff, what can we learn about the mechanism of acceleration of cosmic ray particles by star clusters that can be applied to our efforts to generate high energy particles by accelerators?
Oh, yeah. I think it's, so in the lab, there are all kinds of particle acceleration experiments, especially using plasmas and also kinetic waves. And the real wonder here is, from what we see from the nature, the acceleration could be much more complicated than the conditions we see in the lab. And there are, for example, in the stellar clusters, we know there are winds in those regions, but those winds typically do not have a very fast speed, but somehow they are very efficient in making particle being accelerated. And these winds, usually in the lab, you can have very coordinated magnetic field, and or if you want to do it in a kinetic way, you have some very nice contained, either like kinetic way or magnetic field to make the particle pushing through a linear path and accelerate them. But in the nature, we do not have those things. It's just a bunch of randomly bursts of stars and active, like starburst activities, blowing a bunch of winds in one direction, winds in the other direction. So it's quite a mystery and a wonder that these nature accelerator can be so efficient in making these charged particles to such high energy. And that's definitely an interesting frontier of the studies of particle astrophysics, specifically how they get accelerated.
Thank you, thank you. A question from Philippe and then Aikia. So Philippe asks, is there an upper limit to the energy that cosmic rays can attain?
There's no real upper limit, except that the particles cannot exact the Planck scale, which is even 10 or 9 orders of magnitude above the observed flux level, the observed energy level. But so far the highest energy we have been seeing is a few times 10 to the 20 electron volts, I think. And there are new records being produced by both OJ and TA. So as time goes on, they see more and more events at a higher energy because they have seen more and more longer time. And these new events seems to like refresh the records more and more. So we do not know yet if there's a hot cut on this energy of the individual particles.
Thank you. Next, and please let me know how to say your name. Aikia, go ahead.
That's about correct.
Thank you.
Thank you for your talk. I really enjoyed it. As again, a little bit went over my head, but I try to understand as much as I can. I've got a couple of questions. So what do the cosmic rays like? Do they tell us anything more about the source of their origination? Like, do they give us any more information, any new information about the source? And my second question would be the application of those. Like, do we have, how harmful are they? Or like, what do the scientists have to have any caution with regards to astronauts, or what sort of caution do we have, or are they harmful at all?
Yeah, yeah. So they are definitely bringing more information as being more and more being detected. Like these particular plots showing up front on the screen is a relatively new result that's not known before 2018, 2019, after 15, 16 years of detection, that you accumulate enough statistics to find some significant conclusion that these events come with particular direction preferences. And these tells us more and more about where the origin of these particles are, which is a fundamental question in understanding the cosmos. As of the second question, the radiation definitely exists all over the energy ranges. And the particles we're talking here are the tail with the highest energy, but they are the rarest. That's why you have to build up a 3,000 kilometer square detector and waiting for 2 decades for 5 events at such high energy to arrive. So the chance of having an astronaut, like someone in the space, to being hit by such a particle is extremely small. The harm of the cosmic ray radiation is usually coming from much lower energy. That is not that's very different from the energy range that we're talking here.
Okay.
Thank you.
Philippe texted that he has a question, but he hasn't written it yet. So if you want to just speak up, you may. Oh, here it comes. Number 1, do you feel that we have identified all possible sources of cosmic radiation, or is there room for more phenomenon that are not yet identified?
I think there are definitely room, like this mini black hole next door and the star clusters are not previously proposed as cosmic ray sources. And people have typically thinking about those supermassive black hole jets and neutron stars as the sources, but we ended up seeing these new type of sources that are drastically different from that expectation. So yes, new things are still being discovered.
Wonderful. I see Scott has a hand up. Let's hear from Scott. Scott, you need to. There you go.
I'm sorry, that just took a moment. Can you hear me?
Okay. Yep. Go for it.
Dr. Fang, thank you so much for your talk. I had a question about the chart you put up, with the one with the angle in it, I think you described. On each point, no, this is it's an earlier slide. It's the
it was the red line on the, I think 11.
Yes, that's correct. So can you explain the numbers on the points versus the y-axis?
Oh, so yeah, the number on the points are essentially the actual numbers you see in each energy bin. Say if you're looking at 10 to the 18.9 and 10 to the 19, the events is like 7,585.
Okay, so that's the number of observations.
That's the number of events you receive with your detector. And that tells you the arrival rate of these particles from this particular region of the sky you see. And then if you convert them to the actual energy carried by these events from a particular, from the unit solid angle of the sky. So you see, like say 2/3 of the sky in total, that gives you this many. If you want to ask yourself, what's the unit area of the sky? How much of them is emitting? You divide by the solid angle you see. And also you correct that with your exposure, because the detector does not have a uniform scene. As the Earth rotates, there are some portion of the sky you see more and some fraction of the sky that's gradually going off your field of view, so they have a smaller angular, smaller effective area. So you have to correct those effects. And the y-axis, the curves essentially is showing the corrected flux you see from unit time and unit area of the sky.
Okay.
So
thank
the
you.
curves essentially is instrument independent, whereas the points are particular to the OJ observatory.
Okay,
Okay.
so thank you.
Very good. Another question comes in from Philippe. If we were to entertain long duration space travel, would cosmic radiation be a cause for concern to spacecrafts and humans within them?
Yeah, there are radiation. That's a dominant concern for space travel and the International Space Station, for example, for protections of the astronauts. But the cosmic rays we are looking at here, and these ultra-relativistic particles, they are extremely rare, as we mentioned in the previous answer. They do not cause particular harm to people because it's extremely low chance to encounter one of them.
Mm. Well, that's good. Would we have any further questions? I'm not seeing any. Well, I think Linda, would you like to unmute yourself? Let's see. How can I help her do that? Ask to unmute.
Thank you for an excellent talk.
There we go.
Yes,
There
thank
we
you
go.
very much.
Yeah,
Sure,
excellent.
it's a great pleasure to be here and got
Oh,
lots of
thank
great
you.
questions.
Thank you very, very much. And I'm pleased to see that you were also inspired at a young age by looking through telescopes.
Yes.
That's one thing that we'll remember for sure. Thank you so very, very much.
Sure. Thank you, and hopefully I'll attend one of your future events where I will be in the Bay Area.
That would be great.
Cool. Thank you.
Thank you. Good
And
night.
thank you, and
Yeah,
thanks
good night.
everyone for coming as well.
Good night.